Hello, my name is Charles Camarda. I worked for NASA for over 45 years as a research engineer, astronaut who flew on the return-to-flight mission following the Columbia disaster, was director of engineering and senior advisor for innovation and engineering development. I am the founder and CEO of a nonprofit corporation called the EPIC Education Foundation, and am visiting and working at the University of South Australia to help develop and grow the EPIC Challenge program in Australia. The EPIC Education Foundation was created to increase the number, rate, and excellence of students entering the job market with science, technology, engineering, and math, STEM-related fields. We totally acknowledge the influence and need for the arts in this process, and so we prefer to use the word STEAM-related outcomes, which are necessary for the innovative solution of complex problems. Our program uses the concept of EPIC challenges to excite, inspire, motivate students, to align students of all ages with their specific passions. We use an innovative conceptual engineering design, or ICED framework, and rely on phenomenon-based learning and problem-based hands-on learning pedagogies for instruction. We tap into the natural human desire and intrinsic motivational drive to solve problems and to seek out the next level of difficulty to test one's ability to learn from failure through discovery in a psychologically safe environment. Real-world challenges of EPIC proportions are posed. They are decomposed into appropriate-sized learning concepts and are integrated into an exciting story or curriculum to create a knowledge roadmap which relates directly to the problem, which links current ideas or knowledge to prior existing knowledge in a meaningful way. Our strategy is simple: capitalize on existing effective educational products, organizations, and technologies to search and curate existing learning objects and content, to develop world-class lessons and programs using an open agnostic software platform, which is lean and agile, a stone soup approach, and an open innovation business model. Please join the University of South Australia, UniSA, and the EPIC Education Foundation to collaborate with our engineers, scientists, and learning analytics team at the Center for Complexity and Change in Learning, C3L, to help transform the way we educate around the world. Lesson 1 is our course introduction and outline. Hello to Lesson 1, the introduction to the ICED methodology. My name is Charles Camarda, and this is a course on innovative conceptual engineering design. This will be the foundation which will be used by students as they conceive, design, and implement solutions to complex engineering problems, which we call EPIC challenges. My name is Charles Camarda. I am currently the founder CEO of the EPIC Education Foundation. Prior to my retirement from NASA, I was a senior advisor for engineering development at NASA Langley Research Center, and prior to that, I was a research engineer and astronaut who flew as a mission specialist on STS-114, the return-to-flight mission following the Columbia tragedy. I later served as Director of Engineering at NASA's Johnson Space Flight Center. This is an introduction to the Innovative Conceptual Engineering Design, or ICED course. ICED focuses on the innovative solution of real complex multidisciplinary problems which are science, engineering, and/or technology-based. It is a result of over 37 years of experience solving tough engineering challenges at NASA and over 10 years teaching the methodology at the professional engineer, graduate, undergraduate, and high school student levels. This is an outline of today's short course introduction to the online course. It will briefly describe the ICED methodology, its origin, why it was developed, and what it hopes to accomplish, and the learning pedagogy that we will be following to help students learn and apply the foundational principles. The course will rely on a hands-on, blended, experiential learning pedagogy similar to problem-based and phenomenon-based techniques. We will use case studies of real-life problems to explain principles and use a hybrid multimodal approach and blend guest lectures, videos, reading assignments, and product development strategies and to assess comprehension and ability to apply the knowledge that we have learned. I will also try to explain what I mean by epic challenges and why it is important. I will describe the science and research engineering design processes and technologies and techniques we use to capture knowledge and how we learn and close what we call knowledge gaps. The process will follow a building block approach to structural knowledge structure development and knowledge capture. Students will learn how to use concept mapping to structure knowledge, link it to relevant past knowledge in meaningful ways, and how to map it to future knowledge which needs to be mastered. During this process, students will learn the importance of failure in discovery and exploration of the problem and critical ways to learn from failure. We will be using what we call an intelligent fast failure approach. At the end of this lesson, students will be able to understand what the ICE methodology is, when it was developed, and why it was developed. What differentiates the ICE methodology from other systems, engineering design, and product development strategies, when to use the methodology, understand what problem and project-based learning and phenomenon-based learning methodologies are, and how they will be used throughout this course. Another objective is to understand the meaning of what an epic challenge is and why it is important. Understand in a very broad sense the methods we will be using to capture knowledge and how it will be validated. Students will be able to understand in a broad sense what is meant by a building block approach to knowledge generation. So this is our logo for the ICE methodology. We will talk a little bit about the origins of the methodology, why it was initiated following the Space Shuttle Columbia tragedy in February of 2003. It was apparent then, after the accident, that we needed to train our junior engineers at NASA to better understand and to work together with faculty from some of the top universities in the U.S. like MIT, Georgia, and Penn State. We developed this methodology with these professors in a program in 2008, and we taught this to 30 young or junior NASA engineers in an intensive one-week course. During that workshop, we specifically focused on an epic challenge that NASA was struggling with, the safe land landing of the Orion capsule. So, like I said, we began this program after the Columbia accident. During the launch of STS-107 on January 16th, I was an astronaut training as a backup crew member for Expedition 8, the 8th expedition to the International Space Station. It was during that launch that we realized that a large piece of cryogenic foam that you see here had broken off of the external tank, a piece of foam called the bipod ramp. It impacted the orbit of the vehicle, as you see, and struck either the wing leading edge, which was made of reinforced carbon-carbon, or possibly hitting the fragile fibrous ceramic thermal protection system tiles. So we really couldn't tell from either of these figures, from either of these videos, exactly where the foam hit. We were unaware that this had happened during launch, and we were alerted to this only after we found out that the crew, we lost the crew and we lost the vehicle during re-entry through the Earth's atmosphere on February 1st, 2003. When the NASA mission management team assessed the criticality of this event, they made the incorrect determination this was not a serious problem and the vehicle was perfectly safe to land to Earth. In my mind, it wasn't a technical failure, the foam coming off, it was a failure of imagination. Imagination on the part of the crew on the ground. They failed to ask a critical question: what if a large piece of foam came off the vehicle and it hit someplace critical on the vehicle? Because we had experiencing foam coming off the vehicle throughout the entire life of the vehicle, even 20, 30 years prior to this accident. The crew on the ground had to make a decision. We know now that it was a flawed decision, which cost the life of 7 crew members and the destruction of the space shuttle vehicle. The Columbia tragedy was a technical failure. However, just as important as the technical problem is understanding what led seemingly intelligent engineers and program managers on the ground to grossly misdiagnose the problem, the severity of the foam impact, and its ultimate resulting loss of the vehicle and crew over Southeast Texas. The mission management team and other specialist team contained some of the best systems engineers and system thinkers, program and project managers, or did they? This is a stark example of why we need to change the way we think and the way we educate. This, in my mind, was was not a failure of just technology. More specifically, a foam strike. It was a failure of imagination. We are talking about predominantly left-brained individuals, engineers, who follow rules, processes, and procedures which they believe will guide them and keep them safe and ensure safety and good decision making. It was totally wrong. This was a failure of imagination, as I said earlier, more importantly, critical thinking. There was a total lack of critical thinking skills by the team on the ground. They did not question their assumptions. And imagination. Imagination is the ability to conceive that which is not, to ask the question, what if? Although large pieces of foam had been coming off the vehicle and were breaking off during the launch, no one asked the question, what if? Or was passionate enough about finding the answer to such critical questions. What if the foam hit a fragile piece of TPS or insulation? There was a failure of communication within the agency, where relevant information was not transparent to key individuals that were truly expert within NASA to help make decisions. We had the right people at the research centers at NASA to help Johnson Space Flight Center and their engineers to make this critical decision, but we did not access them and get their inputs in order to make this, before they made this decision. It was also a failure of culture, of mission managers who never fully understood the importance of failure. It was also how we structured our organization, the hierarchical structure of our organizations, which we will discuss throughout the course. This very highly siloed hierarchical structure prevented or impeded the flow of critical information up and about throughout the agency to help us make these decisions. Also, the environment was not psychologically safe, okay? So experts that were available could not raise important questions and dissent without express dissent with existing views without fear of reprisal or recrimination. Purpose of this course is to educate students in these mistakes and to teach them how to work together as highly effective teams to ensure these issues do not reoccur. I'd now like to talk a little bit about the history or the origins of the ICE methodology. This slide shows a condensed early history of the EPIC Challenge program and the development of the ICE methodology. As I said, we began this process putting together and formulating these ideas right after the Columbia accident. During that time, we had to look at different ways to ensure the safety of the crew on that next flight. This was before I knew I was going to actually fly on that mission. And so, one of the issues that one of the technologies we had to develop was a way to fix a wing leading edge, which was potentially damaged by debris during launch, but using a crew of spacewalking astronauts. And so we'll talk a little bit about, during the course of this presentation, this course, we'll talk a little bit about some of these case studies, these examples, this RCC repair team, and what we were able to accomplish. We did this working in my friend Don Pettit's garage off-site, this laboratory where we demonstrated by doing this with a very small team, we could solve a very difficult problem that NASA and its contractors, Boeing, Lockheed, and Thiokol, were struggling with. We actually invented technology which we flew on my mission, the return to flight mission, in 2005. In 2008, I was asked to teach these techniques to young NASA engineers. And so we had to develop a curriculum of study in order to do that. We were looking at 30 young junior NASA engineers from 7 different centers, and we built a team of faculty from Georgia Tech, MIT, and Penn State, and also subject matter experts from NASA, and we developed what we call the ICED methodology. The epic challenge we chose to work on, we developed this methodology, as you see here. The epic challenge we chose to work on was the safe landing of the Orion capsule, a program NASA and the United States industry had struggled with for over 50 years. So we put together these teams, and as you see here at Penn State, these 30 young NASA engineers, we went through this ICE methodology process, and we came up with dozens of ideas which could potentially solve this problem. Briefly, this is the curriculum of the ICE methodology, and we go through it in various stages. From the first stage is really the team knowledge capture phase, where we teach students how to define the problem. We use techniques like functional decomposition. We immerse the students in the problem with a team of NASA and industry subject matter experts. And more importantly, we teach the team how to work effectively as a team and to share information. We call this the knowledgeability portion of the ICE methodology. In the next section, we'll talk about is the idea generation, okay, where we basically look at multiple ways of teaching creativity and different methods for teaching creativity. We call that the ideation phase. The next phase of the methodology, we teach students how to rapidly mature multiple ideas simultaneously and do not down select to one particular specific idea. We use techniques like rapid concept development and intelligent fast failure to select multiple ideas only after we've sufficiently reduced the knowledge gaps, how much we understand about these different concepts, so that once we make that final decision, we're 99% sure that those ideas we could produce and they will solve the problem. The primary focus of the ICE methodology is really during the conceptual design phase, is to compress this time to conceive and rigorously evaluate ideas through rapid, intelligent analysis, prototyping, and testing in order to select intelligent concepts early during this conceptual phase of product development. This is the phase of where most industries and NASA suffer the most. We typically will identify and select one concept too early. We have large knowledge gaps, and then we fail somewhere downstream in the development cycle and then have to repeat this process. This causes excessive programmatic delays and exponential rise in cost. This is a notional concept of the phases of the ICE methodology and how we would teach it. Although it appears the phases follow each other in a sequential fashion, in reality, all phases overlap to some degree. And key principal skills are sequenced throughout the process so that they can be learned, understood, and applied during the solution process. We use this problem-based learning approach, and we create these several different tracks for students to become proficient in knowledge capture and literacy, searching and curating knowledge. We teach them different creativity skills which they can master and apply throughout this process, and we teach them how to work together as a team. We follow the Confucian mantra of I hear, I forget, I see, I remember, I do, I understand. Learning by doing in a problem-based or phenomenon-based learning pedagogical approach. The other phases of this project deal with the rapid concept development. And so in addition to other concepts that we teach program and project management. And we teach the students how to fail. We teach the students how to, intelligent, fast failure, how to fail smart, fast, small, cheap, early and often. And we call this phase of the learning rapid concept development. So the students are actively getting out there, trying things, failing and learning rapidly, and developing the skills that they need. Professional skills such as systems engineering, program and project management, rapid prototyping, concept development, critical thinking, and effective communication. So, we use the term epic challenge, and we toss that around a lot, but what really is an epic challenge, and why is it important to create a program called an epic challenge program? It's very different from other programs. We define epic challenge as a very difficult or complex problem which is multidisciplinary in nature and which does not have a current solution. It is one that has several top science and engineering organizations basically struggling to solve. Problems that NASA can't solve, problems that industry can't solve. It could be large enough so that it's of global significance to society, which will definitely require a collaborative team of people to solve. And we connect with these subject matter experts in team-based learning in order to help us solve these problems. Why is an epic challenge important? In my mind, an epic challenge is important because it inspires, motivates, and challenges participants to stretch their capabilities, to learn, collaborate, and innovate to solve difficult problems, and really to be part of something larger than themselves. We see many young students and even older students get addicted to gaming. And why are they addicted to gaming? I believe it's because young students and older students, like myself, want to feel like they're part of something bigger than themselves. We think these large challenges instill a sense of urgency and criticality, which imparts a healthy tension. It builds what we call an esprit de corps, or a camaraderie, which leads and helps lead to high-performing team behaviors. It allows students to be innovative and creative, to fail and learn fast and furiously, and to think and question things critically and all assumptions. When you think about it, the whole idea of an epic challenge is no one else has ever solved this problem. So we shouldn't be concerned with failure if NASA can't solve this problem, and we should, anything goes, basically, right? So, what are some examples of epic challenges? I really believe the epic challenge creates the passion and the environment to sustain the passion. These are just some of the epic challenges that I've had the good fortune to work with throughout my 45 plus years at NASA Langley. These are some challenges that are probably more difficult than even landing on the moon, the Apollo program. These challenges will serve as some of the case studies the students will study from and learn about, which demonstrate some of the principles of the ICE methodology. The National Aerospace Plane on the left, or NASP, was a program to develop a hypersonic vehicle that was totally reusable, could take off horizontally from a runway, fly directly to orbit, accelerate to Mach 25, fly directly to orbit, return to Earth, and turn around and fly again and be ready to fly in 1 week. When you think about it, this is an awesome challenge. We are still not able to successfully design such a vehicle. The next challenge was a single stage to orbit vehicle, fully reusable, which would not have any stages or expendable components like we have now, which fall off into the ocean as we get higher and higher in the trajectory. This has never been accomplished, and current attempts like SpaceX are looking at making these first stages as reusable as possible, these components. But last but not least, we'll go into detail about how we developed a team to solve the challenge that I worked on prior to my mission, and that was the development of a successful repair technique, on-orbit repair technique, to a damaged space shuttle wing leading edge. We were actually able to successfully complete this challenge, and I was fortunate enough to actually fly this repair technique that we developed on my flight following the Columbia accident. And we'll talk a little bit about that and how we were able to not only develop the team, but what it took to rapidly mature those ideas so that we could do it in time for us to fly. The methodology we will be using is called phenomenon-based learning, very similar to problem-based learning, and it follows a different kind of trajectory than Bloom's taxonomy. Bloom's taxonomy follows a linear progression from learning, beginning as shown here, with seeking knowledge, comprehending it, applying it in real-life situations, using analysis and synthesis of that knowledge in order to build concepts which then we can evaluate. You have more of a roller coaster kind of effect, okay? With phenomenon-based learning, this linear progression turns into this roller coaster you see here, starting with the learner basically begins with a phenomenon, a real-life scenario. Person analyzes the linkages with different concepts and subjects, identifies the gaps, what they need to know and understand, what knowledge they need to know and understand, and then seeks out that knowledge, comprehends it for each subject area, and then synthesizes it individually and also together as a team. So essentially, what was a process of construction of knowledge has been broken down into a deconstruction and then a construction phase. First, deconstruct the phenomenon into different concepts, processes, understand them, and then reconstruct them into the original phenomenon and probably draw parallels with other phenomenon. This also means that it could be more learner-centric, as there are no set ways in which the phenomenon can be deconstructed, and hence there is no specific pathway for construction. Each learner will do this in his or her own manner. The number of linkages and the pathways chosen will depend on their prior knowledge. And we will use concept mapping here, developed by Dr. Joe Novak at Cornell, to help the students visualize this process. One of the most important outcomes from this shift in learning will be establishing the relevance of the content to be learned, as the learners will no longer sit with the question mark in their mind as to why they are learning this particular concept. They'll be able to see exactly how it will be applied. They themselves will have established why they need to learn what they are learning in that content or subject to figure out a phenomenon that they need to understand. The relevance of that content being learned will be clearly established, and hence the interest and motivation to the learner will be much higher than in the current subject-oriented approach. This will also signify the beginning and of the end of course books as we know them, and teachers and learners will have to research a phenomenon. They will compile the content dynamically as they keep deconstructing the problem, and they will identify what they need to learn, and they will also choose how best to learn it. Educators can share the curated content using open online open educational resources. They could use personalized learning according to the needs of the learners using the social learning platforms, and this sequence of resources will be the new course book, if you will. These learners will use these OERs in the forms of video, animation, notes, documents, and we will be using this collaborative platform, this online learning platform, to help us teach these students. Here is a list of some of the engineering case studies that I've personally compiled and have been involved with to emphasize the importance of the principles that you'll be learning throughout this course. Each of these problems were of themselves what I would classify an epic challenge program. These challenges were so complex that it is not even certain that there is a solution to these problems. And so these are problems that NASA is currently struggled with or is currently still struggling with. The return to flight of Space Shuttle after the Columbia tragedy and understanding what the cause of that accident was with the damage assessment team, how they created knowledge in order to understand why foam was coming off the vehicle and why it caused a problem. The RCC repair team that I was personally involved with. Single stage to orbit program, which we call the X-33, and the development of a reusable cryogenic tank. We'll talk about that problem. We'll also discuss land landing of the Orion capsule, the problem that we posed to our young NASA engineers. And we'll also talk a little bit about an alternate launch abort system for the Orion vehicle, another team that we created in order to solve another challenge for space vehicles. So, the construction of knowledge. We'll discuss a little bit about how the students will be using a scientific process that engineers and scientists use to help understand problems or concepts. How do scientists and engineers, researchers develop and construct knowledge to understand phenomena that they are observing? We will use a method taught to me by Dr. James Starnes, which uses analytical or numerical models and experimentation to validate physics-based understanding of a problem, testing the failure structurally, these structural concepts, understanding the limits of those designs, and using principles like optimization to improve that design process. So we will show how we go and we construct analytical models, how we conduct experiments, how we use those analyses to help us move in design space. And then once we come up with what we consider to be an optimum design, how we use that design to actually solve experiments. We'll show the students how to systematically vary parameters throughout this knowledge capture and to learn by doing, by failing, and by assimilating that knowledge and understanding mechanisms of failure. We will also use what we call a building block approach in order to do this. Use a building block approach where we teach students that you come up with an idea or a concept, but now how do you develop? You have to look at each concept and look at all the different ways this idea or this concept in your mind on the left-hand side could potentially fail. We then will teach the students how to use a building block approach, going into the laboratory and designing experiments to fail intelligently, what I call failing smart, fast, small, cheap, early and often. Okay? We use this stepwise approach, increasing complexity and rigor in both analysis and test, at each of these different levels in order to mature these ideas. And we're slowly increasing the level of rigor of our analysis and also of our experimental test technique until we're approaching full-scale testing of a full-scale system, and our analyses are now fully developed that we could potentially predict failure of that concept before we actually go in the laboratory and test to failure. Okay, we do this cyclically at each stage. At each one of these stages, each one of these elemental building blocks, as we're slowly building up to a full-scale design, we're developing knowledge on how to analyze what our concept. We go in the laboratory, we test to failure, we're learning how to predict how it will fail, and then larger and larger as we build a full-scale system, hopefully by the end of this process, we will gain enough knowledge in order to understand how our system fails. So, using this ICE methodology, if we look at it and compare it with Bloom's taxonomy and a conventional problem-based learning approach, using the ICED methodology, you can see that this roller coaster takes several different ups and downs because as we develop multiple concepts, we will be evaluating these concepts cyclically and rapidly in the laboratory. So, in summary, we gave you an introduction to the ICE methodology, outlined what the course entails, talked a little bit about phenomenon-based learning and problem-based learning, showed you some examples that we will use throughout this course. We will be using not only these case studies, but also guest lectures by subject matter experts in the field, in industry and NASA, and we will be posing assignments and methods for assessing how well the teams are performing. Talked a little bit about what EPIC challenges are. How do we construct knowledge using a scientific method and engineering, research engineering principles, and a little bit about the building block approach. That's all for this very brief introduction into the course. I want to thank you very much.